Hello and welcome to the Plant Engineering webcast, Motors and Drives, Advantages of Using Adjustable Speed Drives, sponsored by SEW Eurodrive. I'm your moderator, Amara Razgis, and I'm happy to join you today on behalf of Plant Engineering and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or an endorsement by RCEP. All right, here's an overview of the course. We are going to cover a lot today. Selection of proper motors and drives will be discussed, and energy efficiency will be touched on. So I want to kind of give you a run through of today's learning objectives. Today, you should learn all about adjustable speed drives, or at least as much as we can cover during today's time. When to specify inverter ready or inverter duty motors, applications, and advantages and other items to consider. This event is a live educational webcast presented today, February 16th, 2023. The educational category is technical, health, and safety. All right, so let's go over this platform. If you're having trouble with your slides or the audio, refresh your browser or click the refresh media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need help, type a message in the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources tab on the left side of your screen. And you can type questions for the presenters in the Ask a Question box on the left side of your screen. You can ask questions at any time during the presentation. The Q&A portion will start in about 45 minutes. All right, now we will hear from the sponsor of today's webcast, SEW Eurodrive. At the conclusion, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation.
Getting stressed out by how complex automation can be? Lean on the experts from SEW Eurodrive and check out our MoviKit automation modules. MoviKit is a collection of pre-built software modules for many common motion control applications, ranging from simple drive functions like speed control and positioning, all the way to complex functions like camming and even kinematic robot control. MoviKit makes it easy for engineers of all skill levels to do their own automation. We handle the complex programming part, and you simply enter your parameters and go. Shorten your startup time with configurable automation and motion control functions. No need to waste your valuable time with complex automation programming. Check out MoviKit, the pre-built software modules from SEW Eurodrive.
We've lined up two really knowledgeable presenters for this topic. John Malinowski is an industrial motor consultant and IEEE fellow. He was past chairman of NEMA MG1 Motor and Generator Section. John is a regular presenter and is on the Plant Engineering Editorial Advisory Board. Tim Albers is an IEEE senior member and is a NEMA MG1 Technical Committee chairman. He brings a wealth of knowledge on motor efficiency and experience with industry standards and government regulations. Thank you both for joining me here today. And before we begin, I'd like to get some information from the audience. So this is our first poll. This poll wants to know a little bit more about what you do. What is your basic job duty? So if you could respond to this, let us know. what you do every single day, that would be fantastic. All right, and we're looking at responses here, still coming in. All right, so we have a mix. The majority of respondents today on this webcast are either consultants or design engineers. And we have just a few engineering, maintenance supervisor type folks, but the primary respondent today is either a consultant or a design engineer. So thank you so much. I appreciate your feedback. And John, why don't you take it away?
Okay, thank you, and welcome everybody. Today we're primarily going to talk about energy efficiency with regard to induction motors and synchronous motors. And energy efficiency is different than efficiency, so system efficiency. So we're going to talk about ASD savings basics, and we're going to talk about variable load versus constant load. That's different than duty cycle. Then we're going to talk about some research that NEMA has done, and we're also looking at some DOE research. Tim's going to cover power index, how to use it, and then we're going to look at some typical savings values when we use drives. Okay, what is a power drive system, or a PDS? It could be a one-piece device like an ECM that has an integral motor and drive together, or it could be two pieces, a motor and a separate drive module. In our definition, it does not include the driven load. That's a separate device. So why should you add a PDS? If your system, if your equipment cycles on and off, or the load varies, or it's too loud, or you're throttling it with a valve or a damper, a pump or an HVAC system, or it doesn't operate at full capacity. We all oversize our equipment to operate in a worst case capacity, but rarely does it ever operate at that. It's usually 60 to 70%, so you can throttle it down with a drive. Or if you're always having a lot of mechanical maintenance with breakage and things, the drive can help you out by soft starting.
All right, thanks, John. We're going to move on to our next poll, or our next quick survey. So the question that we'd like you, audience, to respond to is, do you benchmark your energy consumption at your facility? Is it an operational KPI? So if you could give us a little bit of feedback on that, we'd appreciate it. We want to get a feel for what you are doing at your facility to better understand how we should give you information during this education session. All right, so do you benchmark your energy consumption at your facility? Oh, this is kind of interesting. It turns out I don't know and no are almost even. But if you're looking at this overall, all three of them, yes, no, and I don't know, are just about even. So we're working with a variety of folks here in the audience who have a whole bunch of different backgrounds. So thank you very much. Let's move on.
Okay, maybe we can help out with that. Is why is benchmarking for energy savings important? Well, it lowers the cost for energy use. If you know what you use, you know how much you can possibly save. And then a lot of people will say, well, you know, we do cogeneration here. We generate our own power. Well, if you're doing that, in a lot of cases, you're actually selling the surplus of your power back to the utility. So if you save electricity in your plant, you've got more to sell. And then it also allows for expansion before you have to increase the generators that you have in your plant for generation. So there's a lot of good reasons to save. Okay, there's some non-energy benefits. Like we said, decreased maintenance. The motor you can set it up to soft start. It gives reduced wear and tear on all the mechanical things. If you've got a lot of things on your conveyor, if you're soft starting it doesn't tip over bottles and make things clunk into each other. You can improve process control by using the drives to, have one from column A and one from column B, and you can adjust to optimize the feed rates from all your basic feeder systems. You've got system connectivity and visibility. You can remotely monitor what's going on. You can see if something is out of spec, if it's overloaded or even underloaded. If something is not feeding into the system like it should, you can set up an alert for that as well. And then a drive basically corrects for power factor. If you put the right drive in, it can be a regenerative drive that takes the surplus energy from an overriding load and put that back on the line. And then again, it compensates a little bit for voltage regulation. Okay, here we're going to get into types of loads. And this is a little bit different than what you might be used to on when we talk about duty cycle. This is not duty cycle. This is variable torque. So variable torque means when you change the speed downwards, like in a centrifugal load, pump, fan, a compressor, it follows the affinity laws. So when the load decreases by speed, by the cube, half speed is like a quarter load. So as the speed goes down, the load to the motor goes down by the cube. Energy savings is directly reduced with reduced load. So in this case, with a variable torque load, one can expect 30 to 40% energy savings when used with this. A constant load is like a conveyor or a hoist or a constant displacement pump. You change the speed and the torque requirements are the same regardless of the speed change. So the energy savings that are easy to see with a variable torque load are more difficult here. You'd have to benchmark it by how many widgets did I produce per kilowatt hour. So that's much more difficult to do, but it's possible. And then there's a constant horsepower. So it's something like a spindle drive. So this is a case where you're running the product above the base speed or the synchronous speed of the motor. As the speed goes up, the horsepower tapers off directly with above base speed. Those are very rare applications. So we're looking at energy savings here with a power drive system. So at 70% flow, we're getting 49% power reduction. So there's a huge energy savings. And if you drop down below 70%, even bigger savings. So this is centrifugal loads again, fans and pumps and compressors. This is not a constant load like a conveyor.
Hey, John, I just wanted to add one comment. If you go back to that slide, the comparison in energy efficiency is actually not in comparison to a fixed speed running all the time unconstrained, but that top level that it's comparing to is actually the throttled. So that would assume that there's a valve or a damper in place. So, you know, if it's a completely unconstrained flow, the savings is even greater. So just pointing that out, that this is actually the savings that John pointed out, which are huge, are actually to a throttled value. So it could even be more significant if you're not even throttling. So.
Yeah, thanks a lot. So now we're talking about variable versus constant load systems. This is not constant torque or variable torque. This is constant load. So a constant load would be if I'm running the motor with the drive at a fixed speed. Again, we said a lot of times the motor is sized for worst case, and maybe optimized feed rate is 70% or 80%. So I always run at that 80%, and running it other than that is not usual. Variable load is sort of a demand load situation. You might run it at 25% or 50% or, you know, whatever flow for shorter periods of time as the demand. And that's more like, you know, you're in a hotel and have a water system. You know, everybody gets up in the morning and takes a shower, so the demand on the pumps are you know, high in the morning, but during the day when nobody's in the rooms, the water supply is low. So that's what we're talking about, variable load versus constant load. So all different types of applications can have energy savings, some more than others. And we're looking at the difference between variable load and constant load. So you can see the difference. There's savings every place here. You want to add anything here, Tim?
Oh, sure. I mean, I think what this shows is in different applications. One of the most unique things here, I think a lot of people have heard about variable load energy savings, and John was pointing out it's 30 to 40%. You can see here it can be as high as 50 or even more than 50%. But one thing that's more unique is this concept that even something that runs on a constant load can actually have an energy savings. And we'll talk a little bit more about that later. But one of the things that makes this so efficient is the fact that very often an induction motor, you know, running at a fixed speed on the sine wave, you know, just running on utility power, has a very specific speed that it's going to run at. And very often the pump or the fan or the compressor's best efficiency point is not at that exact point. So even though the load is constant, and you may even cycle on and off, having the power drive system with a VFD and motor in place allows you to run at that best efficiency point. And running at that best efficiency point is where you get these energy savings of 20, 10, you know, 15, and even up to 38% over, you know, just running on a sine wave. So that's a unique concept, but we have a significant amount of research now, both independent research from some energy advocate organizations, as well as the Department of Energy, that does show that this is the case. So it's kind of a unique concept, and I think that's one of the biggest things that I think we want to get across here is that for variable torque type applications, particularly, even constant load systems can show significant energy savings. So, yeah. Sorry, John, that was a little bit longer than just a little bit.
No, it's good information. And to Tim's point, this data is from NEA, which is the Northwest Energy Efficiency Association. They're an advocate that works with all the utilities out in the Northwest, and I think some in Canada, in Vancouver area. And just to kind of mess with your mind a little bit, in just basically adding a drive with a motor doesn't make something more efficient. It adds about 3% losses to the system for the drive losses. And then it adds a little bit of losses to the motor. So it's how it's used together with the motor and run at a different speed or load or such that is saving the energy. And that's the difference between variable torque applications and constant torque applications. So this is another thing that came up in the NIA work, is we looked at the variable load and the constant load systems and how much savings there was by horsepower. And once you get up to the 20-25 horsepower range, the amount of savings percentage-wise is pretty even. Everybody talks about going from a premium motor, an IE3 level motor, to an IE4 level motor to save energy. Well, the bottom graph there is showing what happens when you simply switch motors out without a drive by going from a NEMA premium motor to a NEMA super premium motor. Yeah, you're going to get some efficiency improvement, but it's nothing like putting a drive on the existing motor that you have in your plant. Okay, switching it over, let Tim take over now.
Okay, thank you, John. So what I'm going to talk about is actually a retrofit or the installation or addition of a variable frequency drive into a system. Okay, so we've already talked about the different types of loads, and one of the things that we made very clear is that we're focusing on variable torque loads, and so in this case, a fan or a pump load is perfect. It could be a number of different compressors as well. So one of the things, there's some kind of best practices, I'd say, that we would recommend. One is to start with an NEMA premium motor, or better, if it's synchronous. Obviously putting the drive in before the motor. And then the second thing is taking out the valve, or at least opening the valve or the damper, making sure that those are not being used anymore. And then adjusting flow, using the variable frequency drive, and taking whatever that feedback was that was going to the valve or going to the damper, and instead of taking it there, now you take it back to the drive. So that means that whatever that set point was based on, flow, pressure, temperature, tank level, it could be any of those measurement devices, okay, that would now come back to the drive. Now, that's assuming that you've got a variable flow system. If you have a constant flow or a constant load system, you wouldn't need a feedback device at all, because you're just setting it at like a best efficiency point and running. So one of the other things that should be considered for the installation of a VFD, which is unique than it is when you're running a motor on a sine wave, is the cabling between the drive and the motor. So it is absolutely a consideration. Keeping that distance as short as possible is always recommended. And there's very specific cabling which is designed for use between motors and drives. There are the drive manufacturers in many cases are going to have specific recommendations on what that cabling should be. One of the best things that I'm going to tell you to pay attention to as part of that is also going to be the grounding system, and how you actually ground from the motor back to the drive and then to the earth ground from both the motor and the drive. So I just tell you there are a number of best practices. We're not going to spend a lot of time on that today, maybe in a future discussion, but just a little bit of input there. A few other things to take a look at, and when you're putting a VFD into the system, there are these things called common mode voltages. I'm not going to get into a lot of detail of why a VFD creates a common mode voltage. Just trust me, it does. And there are some things that we can do in the system to make sure that the common mode voltage does not affect the motor or the system very much. So one is one of the primary ways, again, is the grounding from the motor back to the drive using a high frequency ground that is specifically designed for this purpose. So again, many of the drive manufacturers will tell you what that is and even have some recommendations on what type of cabling that is. But it does take care of all of these issues, the line imbalance, the oscillating carrier frequency, and even, other poor grounding potential. So what I'm going to say is make sure you pay attention to grounding and follow the recommendations of the manufacturer, particularly as it pertains to the grounding from the motor back to the drive. So I'm going to go over just some terms, and I think it's important to know when you look at these terms, so that they shouldn't be scary to you or whatever, just so people understand what they are. So these are some types of adjustable speed drives. One of them is a volts per hertz inverter. So these are the easiest drives. They don't have, in many cases, all the complicated instructions and things like that. It basically, when it says volts per hertz, it's designed to basically, if it's a 460 volt at 60 hertz, then it's half 230 volt at 30 hertz. It just does that. It doesn't have a lot of capabilities necessarily for doing some high-end machine controls, but for a variable torque load like a pump or a fan, it's perfectly suited for that and will do a great job. There is something called an open loop flux vector and a closed loop flux vector drives. In many cases, those drives can be the same, and it just comes down to whether they're connected with a closed loop speed reference or not. The thing is that a flux vector drive can do a variable torque load. It has the capability to run your fan or your pump. It just may have a lot more capabilities than that. So it may be a little more expensive, potentially, and it might take a little bit more to set up because it's going to have a lot more capability. So therefore, it has a little bit more that has to be set up. So some of them, the hardware is the same between a volts per hertz drive and a vector drive. In some cases, it's not. My point is all of these will work for a power drive system. And particularly if you're doing a variable torque load, all of these will work. They just may vary in expense and maybe a little bit in complexity for setup. So let's talk about naming electric motors and what they're used for on a drive. Okay. So, let me start by saying, first of all, most NEMA premium motors are going to be capable of being run on an inverter. Okay. If it's a NEMA design A, B, or C, or an IEC design N or H, they're going to be capable and have an installation system that at least in a general purpose mode will have the capability to run on a drive. And in many cases, you're going to see that the motor manufacturer is going to say that, yes, this is capable and suitable for running on a drive. The question is going to be, what is the term? Okay. There are many, many terms in industry that refer to inverter capable or inverter duty or inverter rated type motors. There is an industry term that the Department of Energy has started to use, which is called inverter only. And inverter only does mean something specific. And what that means is that it's really not even capable of starting on a sine wave. Okay. So if you see an inverter only motor, that's a motor you're going to have to run on a VFD, not really capable of running on sine wave power. Okay. There are a few things about it because of that. The DOE doesn't regulate it, but it's also very specific, usually used for very high speed range, constant torque loads, very specific. Definitely an overkill motor for a variable torque application such as a pump or a fan. So what I'm telling you is most motors are going to be capable of running on an inverter. Be careful of saying I need an inverter only motor or the best inverter duty motor. If you're running it on a pump or a fan, you may not need that, and you might be spending a little bit too much versus what you really need. Okay, next thing is I just want to address from the IEC perspective. If there's some folks that are mostly in the IEC world, there are a couple of IEC standards that do address inverter duty motors, or what they call in IEC converter capable motors. So they're calling the variable frequency drive or adjustable speed drive a converter, converting, I guess, to the speed of the frequency. So one thing is that, there's a couple of IEC standards there. You can see them listed. You can actually, when you get a copy of this, you can click on those and go to those standards. But those are standards for testing of the IEC motors. And again, just to recognize that there's some different terminology within the IEC world, and a converter duty motor will also run very well on an adjustable speed drive, but you may not necessarily even need to have that to be able to run, again, a variable torque load for your power drive system. The equivalent NEMA standard, as we talk about it here, a converter capable motor, the NEMA standard is this part 30 within NEMA MG1. And that is kind of a general purpose motor, as I talked about before, like a NEMA premium motor running on a drive. And then this converter duty motor is the more dedicated motor, and that's similar to the NEMA MG1 part 31. And I know I can't talk about companies, but NEMA is generic, and so I will make the comment that if you go to the NEMA website, you can actually get the NEMA standard, NEMA MG1, for free. So you can download that and have fun reading through that document. It's a big one, but there's a lot of great information in there. So I'm going to go back to, if you remember from the very beginning of this presentation, when John was talking, he defined the power drive system. And the power drive system, you see right in there is circled in red, PDS power drive system. And it includes the drive modules that make up a full variable frequency drive. And it also includes the electric motor. Okay, so that is the power drive system. Now, a motor system then includes some other things, and starters and contactors and other things that we're not going to talk about here today. And then, when they bring it out to this extended product, that includes things that aren't included in our discussion, but that would be then the pump and the fan and the compressor and those kind of things. A lot of this is defined in an IEC standard. The IEC standard is called 61800-9-2 and also 9-1. NEMA helped write those standards, and we actually utilize those as well. But there is a significant amount of information in those standards about calculating your power drive system energy use and comparing it to other power drive systems, and also comparing it to running something that's actually across the line. So if you have an interest, that goes into a significant amount of detail. But I would tell you that you don't necessarily have to get into that level of detail to understand the energy savings that you got. And I'm going to talk about a little bit about that in the future. But NEMA has a power drive system standard, which helps calculate savings, which is actually simpler than the 6100-9-2, but it also doesn't account for anything except for variable torque. So the NEMA standard is just variable torque. This standard from IEC can do pretty much all different types of applications. Okay, so the next thing I wanted to go over is the fact that we're not just talking about induction motors. So I wanted to go over a little bit about synchronous motors and kind of take you through, what I'm talking about when it comes to synchronous motors. Okay, so two things. First of all, if you look at the little chart over here on the right, this is a 60 hertz chart, and you see the number of poles, the synchronous speed of a motor, and then the asynchronous speed. So when we talk about what an asynchronous motor is, an asynchronous motor, in most cases, we're referring to this cage motor right in the middle of this chart here. And that cage motor, if you follow us across, electric motor, can go drop down to AC motor, then go to asynchronous induction, and then go to a cage rotor. That is your induction motor. That is, 90+% of all the motors that you're going to deal with are going to be that cage asynchronous induction motor. Okay. When we talk about synchronous motors, primarily what we're referring to is you follow the AC motor, drop down to the synchronous induction motor, go over to the right, and there's a few different motors here down here at the bottom. There's switch reluctance, permanent magnet, and synchronous reluctance. And I'm going to tell you that there's a very strong derivative of synchronous reluctance motors called synchronous reluctance with permanent magnet assist, or they would call them SYNRA PM or something like that. So the reason why we wanted to talk about synchronous motors is that power drive systems are absolutely capable of using induction motors as well as using these synchronous motors. Okay. And the synchronous motors actually provide even a higher savings, particularly as it pertains to part load. So I will get to a little bit of that in a minute. One thing that we talked about briefly, John talked about briefly at the beginning, is that this point of ECM and PM, there's a lot of terms for synchronous motors. An ECM motor is not anything special. An ECM motor is just a permanent magnet motor or a synchronous reluctance motor of some type that is then just integrated with a drive. Okay, so when you've got an ECM motor, don't think that ECM is a motor technology in and to itself. It's not. It just means that they've taken a synchronous motor of some type, most likely a PMDC or a synchronous reluctance with PM assist, and they combined it with a drive. Okay, so that's what an ECM motor is, and really nothing else. Okay. One thing I do want to comment on, and that is that the Department of Energy has taken notice of synchronous motors and has also, as part of the latest test rule that actually becomes effective in April of this year, 2023, there is now a defined Department of Energy test standard. There's no efficiency standard yet, but there's a test standard for synchronous motors. So that's brand new from the DOE. And there are a number of DOE rules for end equipment, such as pools, circulator pumps, and some smaller ones like furnace fans for houses and a number of other items, where the DOE has effectively ended up requiring a synchronous motor to be able to get to the system efficiencies. Just recognize that synchronous is definitely a thing, and it's going to continue to be a significant portion of power drive systems that are actually being implemented as we move into the future. As I said, I kind of talked about the pool pumps, the circulator pumps, and I'm going to tell you that in at least commercial applications, synchronous motors are taking a significant share of commercial applications. And when I say that, I'm talking about hydronic pumps, and other types of blowers and things like that within commercial and even agricultural applications. So synchronous is definitely growing. It started in the smaller horsepowers, and it is definitely grown to significantly larger horsepowers. And I think most of us in the industry would all agree that this is going to continue to grow. And so, getting comfortable with synchronous motors and the application of a power drive system with a synchronous motor is definitely going to be much more common. So I just wanted to show some of the, some pictures and applications. I start with some of the pumps here. These are a couple of pumps where we've got some synchronous motors that are integrated in. I'm going to show you a few more pictures here of some synchronous motors. The one thing is that, again, they can be integrated like as an ECM. The nice thing about an integrated motor and drive is obviously you're getting it from one manufacturer, and, it's no field wiring. It's a, good compatibility, should be easier to retrofit. So that's definitely something when it comes to integrated. So that is, whether you call it an integrated motor and drive or you call it an ECM, it's definitely something to consider with synchronous motors. So here's just some pictures, no names of companies, but giving you an idea, this is a synchronous motor. This is actually a synchronous reluctance motor with PM assist, and it's got an integrated drive with it. You're actually seeing it without the end shield on it, so don't be concerned. That's just to show the inside. And here's a couple of other versions. Here's one with the drive actually integrated on the end of the motor. Here's one integrated on the top of the motor. So again, a pump and a fan. Again, synchronous motors, whether you call them ECM or integrated motors and drives, really doesn't matter, but that's where we're headed. So I'm just going to talk a little bit about, some benefits and some drawbacks of synchronous motors. So one thing is that you have to recognize is that a synchronous motor does run at the synchronous speed, which is different than the induction motor. So that does take some planning and recognition that the synchronous motor will run faster. Another thing to recognize is that if there are fluctuations in your system, and when I say not just smooth fluctuations, but quick ones that you might call like cavitation or instability, a synchronous motor might need some other things in the system, such as like the addition of a resistor on the DC bridge, because otherwise it becomes a generator pretty quickly. So there are some things like that to consider, particularly as it pertains to, deceleration. That's what I said. You don't want to turn your synchronous motor into a generator. Your drive's not going to like that. So, there are some things to consider. I would say, work with your motor and drive manufacturers. Make sure you do those considerations. They do increase efficiency. They are higher efficiency, but they are in some cases have some considerations that you have to consider when they're applied.
Tim, just as we're getting into this next one, just if you can go into the details that these are not synchronous motors that people may be used to in large sizes. These are generally permanent magnet rotor type motors.
Sure, John. Absolutely. Yeah, I skipped over that when I was on that previous slide. And the one thing I just want to make sure everybody understands is we're not talking about I was going to say your grandfather's synchronous motor. I have to be careful because I am a grandfather, but what I mean by that is I'm not talking about your 5,000 and 10,000 horsepower synchronous motors that actually have a wound field on the rotor that allow for power factor correction. I'm talking about mostly 500 horsepower and smaller, with a whole bunch of it being 20 horsepower and smaller synchronous motors that usually in many cases use magnets, or they're using reluctance torque. So yeah, exactly, John. So I'm going to reemphasize that here. And we could spend a lot of time on this, but again, I wanted to just familiarize people again that, here's an induction motor. This is the standard over here on the left. It has some rotor slip to it. So it's considered an asynchronous motor. Okay. The ones over here to the right, all four of them are all synchronous products. So this is like an interior permanent magnet. So this would be a PM motor. This is a pure synchronous reluctance motor with no magnetism. Here's a synchronous reluctance with magnets. And here's a switch reluctance motor. So just to give you an idea that, when someone says a synchronous motor or an ECM motor, it could really be any of these technologies that are actually being integrated. There's not just one, and they can actually all be pretty significantly different. So, all right. And really, when it comes to the different types of technology for synchronous motors, there is some advantages and disadvantages to different products, okay? Like, for example, an induction motor, it's very robust, easy maintenance. You can run it on the line, you can run it on a drive, but it's got lower efficiency. It's got higher rotor losses. These synchronous motors have no rotor losses, so that's their advantage. They have zero rotor losses. Permanent magnets got some high efficiencies. But you know what? You have to have a drive, and there's a little bit higher systems cost, and you can have some maintenance issues, and it's going to be a little more complex to set up. Very similar to some of the synchronous reluctance. The other thing is the synchronous reluctance also has a lower power factor. A little less complex because there's no magnets in it. So there's always trade-offs between efficiency, maintenance, cost, robustness. So what I'm going to tell you is there's not a single technology that is a solution for everything, but there are going to be some advantages and disadvantages to each. One thing I did want to cover here, and this is just got a couple of charts that show the same thing, but in a different way. So if you look at the next chart and say, I think that tells me the same thing, it does tell you the same thing, but I just wanted to show it in a couple of ways. And this has a pump or a fan curve on it. And what it shows here is, if you look out here at full load, you're going to save maybe 5 or 6% in efficiency, might even only be a few percent in efficiency if it's a larger horsepower at full load of a synchronous versus an induction motor. But if you come down here to a part load, okay, if you're down here at 25% load, okay, you can have as much as a 12% gain of efficiency on the synchronous motor versus the induction motor, because the synchronous motor maintains its efficiency as you slow it down on a drive better than you do on an induction motor. Okay, so when you start talking about 12 points of efficiency gain or even more, it is extremely significant, the difference of applying a synchronous motor versus an induction motor. Okay, so the next chart basically shows the same thing. This is a much larger horsepower. The one I showed previously was a 5 horsepower, I believe. And this one is 100 horsepower. So you can see again at full load here, this is the 100 horsepower. It's only, half a point of efficiency savings. You're like, well, that's not a big deal. But down here at the part load, okay, it's gone from a half percent up to 1.5%. So it tripled in your savings. And here is the induction motor. So, these are a couple of different types of induction motors. And this is your standard NEMA premium. So, you're going from a couple of points to as much as almost 7 points of efficiency. I'm sorry, 3.5 points of efficiency over here. So shows the same thing. It's just a little bit different scale and what the synchronous motor can bring to you. The last thing that I wanted to cover, and just one last advantage of a synchronous motor, is the fact that it does have a little bit more maintenance and reliability capable. And one of the reasons why is because the rotor doesn't get hot. So this actually shows you an induction motor on top and a synchronous motor on the bottom. They're actually the exact same electrical design. One is running with an induction rotor and one with a synchronous rotor. And you can see the heating difference here, okay, between the two. And one of the big deals here is what gets to your bearing, okay? Your bearing is actually going to get some of the heat from this rotor, and on your synchronous motor, it will not. So it's just one of the incremental advantages of synchronous motors that a lot of people don't take into consideration. And I think it's important because it will give you an extended bearing life. And that is still the #1 failure mode for electric motors. So and that's it.
All right, fabulous. We have just one more poll question to ask you. So if you would please reply to this final question, I'd appreciate it. The question is, what's your primary business or industry? And we're looking for this because we're going to give you some examples and some applications, and we'd like to ensure that we have the right information and we're giving you the right feedback. So if you could please let us know, what is your primary business or industry? Let's see here. Wow, we've got quite the mix. So folks are from a whole host of different industries, but it looks like the primary is automotive, transportation. We've got some instrumentation folks here with us today. And then, okay, so we've got some mining and chemical. So fantastic. Thank you so much. We do appreciate your feedback on that. And thank you, John. Thank you, Tim. That was a lot of really good information. And we do have some time to answer questions from the audience. So please type your questions for today's presenters in the Ask a Question box on your screen, and we will get to as many as time allows. Within a few days, this presentation will be available on demand for viewing, along with a link to the quiz for potential PDH credit. We'll post an archive on the Plant Engineering website, and we'll send you an email with a link to this in case you'd like to come back and look at this once again. So, gentlemen, we are going to begin taking questions now. And John, this first question is for you. Can you talk briefly about VFDs and stray voltage causing issues with motor shafts or bearings?
Yeah, there were quite a few questions about circulating currents in a motor and shaft grounding brushes and such. We normally see those in systems that are not well grounded, where a shaft grounding brush needs to be added. And a shaft grounding brush is sort of a Band-Aid that doesn't address the shaft or doesn't address the main grounding problem. But when you're in a commercial building, a lot of times they don't have the same robust grounding practices that you might have in industry. So we can use a shaft grounding brush that's usually on one end of the motor. Alternate to that, you could use a ceramic bearing insert that would insulate the bearing from the frame, or use a bearing with ceramic balls. Two downsides on the ceramic aspects. The ceramic bearing insert sometimes had a tendency to crack. And then in those cracks, you kind of get a carbon dust buildup that's conductive. So that kind of goes away. The ceramic ball bearing is a good solution. However, they're expensive. And in larger sizes, they're quite difficult to source. You want to add some in there, Tim?
No, I think that's a good answer. There's a lot of solutions now that are potential for circulating currents, and there's some standards that people do apply now with insulating. However you insulate at least one end of the motor, and then providing a shaft grounding system of some kind. And there's lots of options for that now that didn't used to exist. So the other thing that does exist now is there's also a number of manufacturers. I'd say most of the larger manufacturers are also capable of putting a shaft grounding device inside of a hazardous motor. So you even have a potential solution here for your hazardous product, which didn't used to exist. So.
And to that point, a lot of manufacturers have motors with shaft grounding brushes available from inventory. It's not something that's special.
Right.
It has to be added later. So a lot, particularly in the HVAC portfolios, and a lot of manufacturers on their inverter-only motors have added a shaft grounding brush.
Right.
All right, fantastic. Thank you, gentlemen. Moving on to the next question. Tim, I'm going to direct this to you first. How do I determine the speed for optimum efficiency?
Yeah, that's a good question, and I kind of referenced it a little bit quickly. You're going to have to work with the pump or fan manufacturer. There is going to be a pump or a fan curve, and if you're familiar with reading those, you'll be able to point out the best efficiency point on that curve, which then will give you the speed versus the flow that you need. A quick discussion with your supplier or even your distributor will give you that answer. So that's how you need to do it. It gets a lot more complicated if you're dealing with an older piece of equipment and you don't have those curves. Can't answer that now. There are ways to do it. But if you have that other stuff, then it makes it a lot easier. So.
Good. Okay. Next question. John, I'm going to send this one over to you. How does the improved motor efficiency affect the inrush current of the motor?
Oh, that's an interesting one. This is something we've been pulling our hair out You can tell by both of us that we've done a lot of that over the last few years. As you change efficiency, we either have to have inrush current go up or starting torque go down. And nobody wants starting torque to go down, so inrush current's gone up. Our charts in NEMA MG1, we adjusted a few years ago and raised them by up to 15% on design B motors. And as DOE is pushing us to the super premium IE4 levels, you will see a new category of inrush currents come out that we're going to model after the European IEC standard, and they'll be called a design BE motor. There'll also be a design CE, but it will still be at a premium efficiency, but it'll allow for the higher inrush currents. Presently on premium efficient design C motors, they exceed the allowed design B inrush. So most manufacturers call them design A motors with design C torques. We're trying to get away from design A motors, which are undefined. We think propagating industry with more design A motors is an electrical safety hazard waiting to happen. So we want to quantify what inrush currents are so that the proper starters can be selected.
Fantastic. Thank you. Tim, this next question goes to you. Why would you combine a synchronous motor with a drive?
Well, I think that's something that we talked about a little bit earlier, and most synchronous motors, there are some synchronous motors that can run, across utility power, but the vast majority would be optimized by running on a drive. And the point is that putting the synchronous motor and a drive together, there are a number of manufacturers, both motor and pump and even fan manufacturers, that are starting to do the combination of the motor and the drive, synchronous motor and drive, and even the final application, pump or fan or compressor, and they're selling them as systems. And the reason why is because they're able to then, as a system efficiency, as a total power use to get out, to get things out, they're actually optimizing with the synchronous motor and drive. So that's the primary reason. People are actually able to hit the lowest power usage for the output of whatever they're trying to do by implementing those together. That's it.
All right. Thank you. It looks like we have time for just one more question. And John, this is kind of a question that's been asked a few times by our audience members here. So it's a little bit longer. And this is talking about grounding rings. When do you need to install them to protect the bearing? And when do you specify them in general? Can you elaborate a bit on that?
Yeah, I think we've answered that one already. That was the first one that was asked. It's a shaft grounding brush.
Okay, let's take that on to the next one then.
We can make another one.
Yeah, we've got a lot here. When you're retrofitting a drive, does the motor need to be rated for inverter duty?
Okay, depends on the application. This gets into what Tim talked about, where it's inverter capable, inverter or inverter duty, or inverter only. DOE calls it inverter only. Is it going to be a motor that you're going to need extreme high torque throughout the speed range? Maybe operation above base speed with constant horsepower range? Something akin to almost a servo motor type of an application, more torque oriented than horsepower oriented. Most motors, even TEFC general purpose motors, we call them inverter capable. CSA makes us put inverter duty on the nameplate. Those motors that have gone through the CSA for Canada will have both variable torque and constant torque speed ranges on them. So you know what you're getting even on a general purpose motor. And I would say that the vast majority of applications, you know, a general purpose motor or even like an IEEE 841 motor or whatever people call their motors for severe duty, outside duty, like chemical process duty, you know, those motors are all capable of running any kind of variable torque load. And on constant torque load, it will depend. Smaller motors have a little bit more headroom as far as temperature rise. And as you get into larger motors, a larger motor might only, you know, several hundred horsepower, might only be able to do constant torque 2-to-1 or 4-to-1. So it's really, you know, you need to really talk to the motor manufacturer and figure out how you're really going to use the motor. You want to add to that, Tim?
I think you did well.
Yeah, thank you. A big thank you to our presenters, John Malinowski and Tim Albers, for today's presentation. And obviously, we did not get to all of these questions, so we'll answer as many as we can offline. And another thank you to our sponsor, SEW Eurodrive. Before you log off, we do need your feedback to improve things. A couple more poll questions will pop up on your screen as soon as this webcast ends. Please take a few seconds to answer them. Finally, on behalf of Plant Engineering and CFE Media and Technology, thank you for joining us, and we'll see you at the next webcast event. Goodbye.